All right. Hello, everyone, and welcome to our webinar. Today, we're going to be discussing meshing and running a high-fidelity aircraft simulation in just a matter of minutes. My name is Travis Kerrigan, and I'm the Manager of Business Development at Pointwise, and I'm joined today by Chichi Wang and Feilin Jia of FlexCompute, the developers of the Flow360 CFD solver. And together, we worked on a benchmark case to demonstrate how well our two tools, and in particular, Pointwise version 18.4, which was released just last month, and Flow360 work together. So thank you both very much for joining me today. The benchmark case we chose is the NASA Common Research Model wing body tail configuration from the 4th AAA drag prediction workshop. We chose this case because it's a representative aircraft model and cruise configuration with a ton of data for us to compare against to really ensure that our results are accurate. And in addition to running our tools out of the box, we did do a grid convergence study and we'll present those results as well. And for those interested, the Reynolds number for this case is 5 million at a Mach number of 0.85. Now, before we get into the nuts and bolts of making the mesh and running the simulation, I wanted to take just a few moments and introduce Pointwise the company and product to those who might be unfamiliar. So with that in mind, Pointwise the company was founded in 1994, just a little more than 25 years ago, and we developed a single product called Pointwise that's primarily used for CFD mesh generation. And I say primarily because we do have clients using Pointwise for other applications like computational electromagnetics, laser etching, and even some finite element analysis. Now, Pointwise is known for the level of control that we provide over the meshing process, our flexibility to work with various CAD packages and export to pretty much any CFD solver, and our expertise in technical support. And what this really means is that Pointwise provides the tools necessary to generate the meshes that you need to achieve the accuracy that you require out of your analysis process. And while meshing has the most significant impact on solver convergence and accuracy, we certainly understand that meshing isn't the most glamorous part of the analysis process and is simply a means to an end. The reality is that the most important part of the process for an analyst is, well, analyzing the results and making informed engineering decisions. And to do that efficiently, moving forward, automation becomes critically important. In fact, the CFD Vision 2030 study put it best in that the mesh generation process should ultimately be invisible to the CFD user, and we couldn't agree more. And no, this doesn't mean that we're out of a job. What this means is that we have to take the control and flexibility that we're known for and really marry that with our decades of expertise and deeper automation beyond just glyph scripting. And this is actually what we've been really hard at work on at Pointwise, and our solution, we call it Flashpoint. This is our answer for intelligent, goal-based automatic meshing. And in Pointwise version 18.4, we released the first in this suite of features targeted at the surface meshing process. So with that, I'm going to go ahead and talk a little bit more about the mesh generation process for this benchmark case, starting with geometry preparation. Now, in the image that you see on the top, this is the CRM geometry as imported, where each color represents a different trim surface in the model. Now, all of these surfaces together form kind of a watertight analytic representation of the aircraft, but each one of those trim surfaces isn't exactly where we want to provide mesh control. These surfaces aren't where we plan on applying boundary conditions. They don't really represent the engineering intent, okay? They're an artifact of the CAD process, the geometry creation. Now, through solid modeling and quilting in Pointwise, we arrive at what you see on the bottom, where each color better captures the engineering intent, okay? We have a surface for the fuselage, fairing, wing upper surface, wing lower surface, areas where we plan on applying mesh attributes for control, but also applying boundary conditions for the solver. And this is really the prerequisite for the new Flashpoint surface meshing feature set for performing automatic surface mesh generation. Once you're in this task using Flashpoint surface meshing, the automatic surface meshing task in Pointwise, you're presented with 3 tabs like you see over on the left-hand side. The first tab highlighted in gold there is the global tab. And this is where you'll spend the majority of your time in this tool. And in fact, I'll mention that for this benchmark case, this is where we spent our time. We didn't change any of the defaults. Everything that we're going to show you is out of the box. The only thing we changed was the surface meshing algorithm. The default is actually advancing front, and we changed that to quad dominant, but everything else is out of the box. In this tab, you can get a sense for the geometry characteristics, the extents, symmetry boundaries, any gaps or cracks in the surface. You can set the resolution of the mesh, some goals that you want the mesh to be able to achieve, and even examine grid quality from in this tab. Now, if you want a little bit more control, you can go over to the local tab. And in the local tab, you can explicitly pick surfaces or collections of surfaces and assign target edge lengths. You can even set up patterns based on names. So if you've named all of your surfaces upstream in your CAD tool, you can set up a pattern to automatically apply a target edge length to those surfaces. And the nice thing is once you set this up once, you can save off the environment file, load in a new geometry, and it'll automatically reassign without any scripting necessary, which is really cool. Over in the Advanced tab, you have some parameters exposed that control the underlying algorithms for the meshing process. You can run a grid refinement study, which we did, and I'll talk about that in the next slide. And you can even visualize where stretching will be applied on the surface mesh level for, curvature boundaries or convex or concave corners. Now, over on the right-hand side, you can see the size field. This is the target edge length rendered on the geometry before a surface mesh is even created. And this is really handy, particularly if you've specified a lot of resolution controls or you've generated some sources to define target edge lengths in specific areas. You can see how all of these are going to impact the resolution on the geometry prior to the surface mesh being created. Now, on the right-hand side, you can see the actual surface mesh, and this is the coarse mesh variant, again, created out of the box. Now, I did mention a grid refinement study earlier. To run a grid refinement study here on the Pointwise side using this tool, all we need to do is change the refinement factor, and there's a benefit to doing this. Let's say you set up a whole bunch of resolution controls, right? You've set up all these resolution filters to specify target edge lengths on different surfaces. Rather than going and manually adjusting all of those and cutting, let's say, the resolution in half if we wanted to run a grid refinement study, all we really need to do is come into the Advanced tab and just change the refinement factor. And the benefit to doing this is all of that refinement is handled automatically in a very consistent way. And when we're talking about unstructured grid refinement, consistency is key. We need to ensure that the meshes that are being created as part of the grid refinement study are being done in a consistent manner and they're following the same rule set. If we were doing this by hand, it would be really hard to guarantee consistency because we may make different decisions depending on the refinement level. But when we're using an automatic tool like this and we can just change one value, we're ensuring that the meshes are consistent from one resolution to the next, but also are being generated following the exact same rule set. Now on the right-hand side, you can see meshes of various resolutions, the cell counts, and the time required to generate those. All right, so now I'm going to show you some of the characteristics of really the out-of-box experience that you get with Flashpoint surface meshing. And we'll start with the alignment of the quads up near the nose and the fuselage. Like I mentioned, this was really the only parameter that we changed from the default advancing front tri-meshing algorithm to quad dominant in this case. And you can see the nice alignment of those quads on the surface. You can see that if we look kind of mid-span, the transition from anisotropic stretching at the leading edge and trailing edge, blending smoothly into the interior of the wing, kind of mid-chord. We use anisotropic stretching because using this approach, we can more accurately and regularly capture areas of high curvature like the wing leading edge or the blunt trailing edge surface, those convex corners. If instead we used isotropic refinement, we would have to pack a ton of cells along the leading edge and trailing edge for the same resolution. So this is what anisotropic stretching buys us. We can stretch the cells in the span-wise direction, significantly reducing the cell count, but more accurately resolving the geometry. And in practice for external aero, using anisotropic stretching allows you to reduce your cell count by about 2 to 3 times compared to isotropic refinement, which means that if you're running a simulation, you're getting to your results about 2 to 3 times faster, which is quite advantageous. You can see we can wrap really smoothly around features like the wing tip, and then that blunt trailing edge is a long, slender surface. We can automatically apply our structured meshing best practices there to capture that blunt edge and then pack points into that wing root region. And like I mentioned, this is all out of the box, all handled automatically. Now, once that surface mesh is created, the next step is generating the volume mesh. So we grab the surface mesh, we go into our build far fields tool, specify how far away we want the far field, how many layers we want, the growth rate, our initial cell height to target our Y+ value, and go. In this case, we generated a hex core mesh using our voxel meshing algorithm. It's a half symmetry model. You can see that symmetry plane domain over on the right-hand side, and you can see the volume mesh matching it precisely. There's no buffer layer of tetrahedra between the volume mesh and the symmetry plane. And the real advantage here is that we can actually mirror this on export. So if we wanted to run a full aircraft simulation, we don't have to necessarily build it in Pointwise. We can just build half of it in Pointwise, and then on export, going to the solver, we can just mirror this mesh over, and we're not going to have this rind of tetrahedra running up the symmetry plane, which is really nice. Now in this case, this is the coarse mesh variant. Like I said, the node count's 5.5 million, cell count's 9.5 million, takes about 6 minutes to run on the laptop, pretty quick operation. With the volume mesh created, the next step is exporting it. We pick a solver, we set up our boundary conditions, and then we export. This whole process, start to finish, from geometry prep, surface meshing, volume meshing, export, takes approximately 10 minutes in Pointwise. And I was really debating whether or not to demonstrate that or just put it in slides like I did here. Turned out the demonstration is actually kind of boring because I can go into a tool, push a button, get the result, go into the other tool, push a button, get the result, set up boundary conditions, and export. So at least this gives me a little bit more of an opportunity to talk through some of these things for you. But if anyone is interested in seeing that, certainly let me know, and we'll open it up for Q&A at the end, and I'll give you some contact information as well. So with that, I'm going to pass things over to Chi-Chi, who's going to introduce you to FlexCompute, Flow 360, and walk through the results of the simulation. So Chi-Chi.
Yes, this is Chi-Chi Wang. I'm an associate professor in the Aeronautics and Astronautics department at MIT, and I am one of the co-founders of FlexCompute. So we founded the FlexCompute 5 years ago to develop an approach of integrating co-designing hardware and software to vastly accelerate computational simulations. And so far, it has given us unprecedented speed. We are now able to solve a full range solution with 5 million grid points, more cells, in 100 seconds, so a little bit more than 1 minute. And our product has been trusted by companies to fly people and to make billion-dollar products. So Flow 360, go to the next slide, please, is the product we are demonstrating today. It solves a lot of CFD models with the goal of 360 seconds. So what we do is we solve steady and unsteady Navier-Stokes equations using Reynolds average, the Navier-Stokes turbulence model, as well as detached eddy simulations. We have recently developed a rotating frame of reference capability. So we have mesh rotating inside of each other to simulate propellers and rotors. For you to access our solver, we provide a web browser-based interface as well as a Python-based API so that you can automate your entire CFD process if you can code in Python. Next slide, please. So our speed is really unprecedented in the sense of the following. Traditionally, if you want to perform a CFD simulation, you have to access a cluster and decide how many CPU nodes to use. And depending on the number of cores you use, you get varying speed. And at some point, as you give it more and more cores, you reach the so-called strong scalability limit. So you won't go any faster, even if you provide more cores. Flow 360 has broken the strong scalability limit by a huge factor. And we don't even require you to allocate how many cores to use. So we have baked our expertise in simulation into the interface of our product. You just need to give us a mesh and the flow parameters, and the computation is going to be going, everything happening in the background. And with this automated procedure, we give you 73 times speed up compared to the fastest speed you can get in a typical traditional cluster. And we achieve this without sacrificing accuracy. On the right-hand side, you can see our Flow 360 giving you the result as a function of the number of nodes, comparing with other commonly used solvers in the market. And particularly, the red is Flow 360 and the blue is Fun3D by NASA Langley. Next slide, please. The interface you can use is very simple. As I have said, you just need to upload the mesh. For example, the mesh you generated using Pointwise. And in addition to the mesh, you just need to give a very simple JSON file. The JSON file is for a format that is both machine readable and human readable, right? So that you can interface with our solver either in human or with an automated computer. The JSON file provides the Mach number, Reynolds number, angle of attack, etc., for you to set up the flow simulation. Next, please. As soon as the mesh and the JSON files are submitted, you can visualize the convergence of the flow solver in real time. As we have said, one of the cases typically converge in seconds rather than in hours. So you can really see the convergence, the drop of the residual in real time. And through our web browser-based interface, you can also see the convergence of the forces, the lift coefficient, drag coefficient, convergence in real time. And with that, I'm going to show you the result we got with the 3 different meshes generated by Flashpoint in Pointwise using the automated mesh generation. So first of all, this is the causes mesh with 5.5 million grid points. And this mesh converges in 105 seconds in our solver. And on the right-hand side, you can see the surface pressure represented on the upper and lower surface of the airplane. And watch this as we go to the next mesh with double the grid points. So you can see the grid refinement process in the work, and there is a slight alteration of the pressure coefficients. The time it takes for the 11 million grid points mesh is 188 seconds, barely more than 3 minutes. As for our finest mesh, if you go to the next slide, you see the pressure coefficient almost doesn't change anymore, so the grid is converged. And this final mesh with 43.2 million grid points converges in 526 seconds to a tolerance of 10 to the negative 10. Okay, and the next slide, you can see the comparison of our medium mesh result, the 11 million grid point result, against a Fun3D solution with 36 million grid points. And you can see the pressure coefficient looks almost identical. To provide a more quantitative comparison, we go look at the angle of attack, the drag, and the pitching moment computed by our solution at various grid points, various meshes. Because the simulation is done at a fixed lift coefficient, the accuracy of the lift prediction can be seen from the angle of attack plot. In this plot, the number of grid points is plotted in terms of the grid point to the minus 2/3 power, because we are looking at a 3-dimensional grid, and our solver as well as the comparison in Fun3D are supposed to be a second-order accurate flow solver. And when the x-axis reaches 0, that's supposedly an infinitely fine grid. So the more towards the left, the more accurate, the bigger mesh we are having. As you can see from the angle of attack plot, Fun3D and the Flow 360, they converge pretty much to the same result. And same thing happens to the drag, total drag, as well as the decomposition of pressure and the skin friction drag. Right, so if you look at the trend, they go pretty much to the same place. The pitching moment also converges pretty much to the same quantity. And in addition to the conversion to the same quantity, you can also observe that at coarser grid, the Flow 360 actually gives pretty accurate solutions. Right, the coarsest grid is the point on the most right-hand side, and the medium grid, the 11 grid point mesh, is the middle point. So even with coarser grid, we give very accurate results, as can be seen here. So this is really a triumph of both the mesh generation, automated mesh generation, and our Flow 360. Here, I'll pass the control back to Travis, who is going to conclude the webinar.
All right, thank you very much. And thank you everyone for taking the time to watch our webinar today, where we walked through geometry prep, surface meshing, volume meshing, and solution and results for the coarse mesh variant. This is all accomplished in less than 15 minutes, which is pretty impressive in a very automated workflow. We're certain that there are questions. I think I've seen a couple of come in already. If you have any questions after the webinar, I'll leave this slide up, but if you have any questions about the simulation, the application Flow360 or FlexCompute, you can always contact Chi-Chi Wang. And if you have any questions about Flashpoint, Pointwise, or just mesh generation in general, you can always contact me at letstalk@pointwise.com. But with that, we're gonna open it up for Q&A. You can type your questions into the questions dialog box. Like I said, I'll leave this slide up while we address questions. And then when the webinar concludes, if you think of anything else, you can always email us. So let me go ahead and open up the questions here. Let's see. Okay, here's a good question. So the first question we have is, you mentioned automatic control of the structured grid on the trailing edge. How do you go about setting that up in Flashpoint, or do you have to make those domains manually after running Flashpoint? That's a really good question. So the answer is no, it'll get handled automatically by Flashpoint. There's a mapped subdivision ratio parameter in the advanced tab that's automatically set up to detect thin rectangular surfaces, and they have to satisfy certain requirements, meaning they have to consist of 4 edges that have a low, high kind of orientation to them. And then that allows us to automatically detect and apply a structured domain that's balanced properly. In addition to that, the curves have to be kind of the same length so that we're not skewing the cells or coming up with completely different distributions on opposing ends, kind of the same requirements that you would have for any structured mesh that you're creating. But that's handled automatically. And if you have kind of a long, slender surface that you believe should be mapped, but it's not, when you're still in the Flashpoint surface meshing tool, you can hover over that, the mesh on that thin surface, and it'll tell you why it didn't map it. And it may just be because the mapped subdivision ratio needs to be adjusted, and that's over in the advanced tab, and you can use that to kind of control that behavior. If it's not mapping, again, there could be a variety of reasons. Perhaps there are more than 4 curves, or it's broken up into more pieces, that kind of thing. One thing I will mention is that in version 2, the second iteration of Flashpoint surface meshing, which we are hard at work on now, one of the things that we're working on is a new algorithm that doesn't have a lot of those same requirements. It's a little bit looser in terms of restrictions, so you'll be able to apply it in more places. That's a good question. All right, Chi-Chi and Phelan, this one is for you. Does the speed up in the Flow360 solver come from a very extensive computational resources, or is it because of convergence acceleration algorithms implemented in the code?
Very good question. So it is a combination of both software and hardware. As I have showed in the beginning, the principle of our goal is really to overcome strong scaling limit through a combination, actually a co-designing of the software and the hardware. The hardware is not just powerful, it is also designed specifically for running the kind of simulations we are looking at. And the software is written for the hardware.
Okay. Was late to the meeting. Is the video presentation going to be made available? Yes, a recording will be made available and on our website. So if you, like I said, if you were late or you think of anything afterward, you can always review the video and contact us. Good question. How do you apply Flashpoint in an MRF scenario, like a propeller? This is a good question because it's something that we've recently done. So Flashpoint simply requires you to select a model, and you can actually select multiple models before entering the automatic surface mesher. And what it'll do is it'll automatically generate a surface mesh for each model that you have selected. Now, in an MRF situation, and we've done one recently, the FDA blood pump, you basically mesh each model separately. So that MRF interface needs to be a part of the models. You mesh each model, and then you use grid merge to stitch the two together. And that's how you can go ahead and basically mesh multiple models with an MRF interface. It's a good question. Can Flashpoint handle geometry change? Yes. So when you set up Flashpoint surface meshing for the first time, if you don't tweak anything, then that's basically out of the box. Just bring in a new geometry, and you can even push the button on the toolbar that says, you know, Flashpoint, you know, automatic surface mesh. You just push the button on the toolbar and it'll create a surface mesh. If you make changes to the setup for Flashpoint surface meshing, or you come up with any local resolution filters, you can save all of that off to a Pointwise environment file, load that up, load in a new geometry, and again, push the button on the toolbar and it'll automatically apply all of those same things. So if you're making geometry changes, just push the button on the toolbar and it'll remesh using the exact same setup that was used to mesh the baseline case. Is there a PC requirement for Flashpoint? It's the same requirements as Pointwise, and you can find those on our website. Pointwise runs on Windows, Mac, and Linux, and these meshes were made on a laptop with 16 gigabytes of memory, so it's pretty efficient. Do we still need a watertight surface mesh or a watertight geometry for the mesher? Another good question. The prerequisite is a watertight, what we consider a watertight and quilted geometry, much like we prepared in this case. That's the prerequisite to get the best results out of Flashpoint surface meshing. You can still give it, you know, anything and get a mesh, but you may need to do some cleanup of the mesh afterward using like the grid merge tool, for example. And this is something that we've encountered is, you know, if you do some solid modeling operations and clean up your geometry, you may get to a point where there's a part of the geometry where you just cannot stitch it together. You can go ahead and apply the surface mesh on that and then just use grid merge to take care of that last little piece. So you can kind of still use, and maybe I should mention this, one of the advantages with Flashpoint surface meshing, it is a very much top-down meshing tool that provides a lot of automation, but you can still use all of the bottom-up tools in Pointwise to modify that mesh. And that's really important. I mean, we didn't sacrifice kind of the manual tools for automation. They can live together, and they do in Pointwise. You may get to a certain point in the automatic surface mesh creation process where you like what you're seeing, but you want to tweak one or two things. You still have all of those tools at your disposal. Let's see here. Does automated refinement also apply to the volume mesh? If you've created, so the surface mesh is used to create the volume mesh. So anything you do on the surface will be seen by the volume mesh. But if you have created volumetric sources for controlling even more of the resolution on the surface, because you can create like a sphere or a box or any sort of primitive shape as a source in Pointwise and have it pierce the surface mesher will see that and influence the surface mesh resolution, and it'll also see that in the volume. So kind of these volumetric sources can now impact the resolution of the surface mesh when being created automatically, and they can affect the volume mesh. Let's see here. Here's a good question. Let's see if I can maybe break this one up. The total drag totally matches Fun3D. My question is, what could be the underlying cause for the slight difference between Flow360 and Fun3D for the moment coefficient? Is it because the fact that each layer in the mesh are being connected through an interface because of the nature of Flashpoint, or is it something else? Did you also validate the results with some classic multi-block grids? So maybe I'll take the second half of that and say there's nothing particularly unique about the type of mesh that we've created for this aircraft compared with other meshes that we've made in Pointwise. Again, it's just completely automated. But maybe Chi-Chi or Phelan, you could come on and comment on why there might be a slight difference between Flow360 and Fun3D. Did anything come to mind looking at the results?
Do you go to the slide about the pitching moment?
Yes.
Yes. So what you when you look at the discrepancy, right? First of all, I want to point out that we are although we are solving the same equation, we are solving the same Navier-Stokes equation with the same turbulence model. In this case, Spalato-Maras turbulence model. The numerical discretization surely is going to be different. So even with the same mesh, we expected different results. And this is, again, also with the different meshes, right? So we have a mesh difference, we have a algorithm numerical scheme difference. So the result is going to be different. What you need to really look at is the so-called Richardson extrapolation. That is when you look at the several consecutive flow solutions with different meshes, you can start to extrapolate to what the solution would be if I further refine the mesh. And this plot, the reason we are plotting the x-axis as the number of grid points to the minus 2/3 power is exactly for the convenience of that extrapolation. In the sense that if you extrapolate the black line, if you look at the pitching moment, if you extrapolate towards the left until n to the minus 2/3 power hits 0, that is a point when n actually goes to infinity. That's an infinitely fine mesh, right? So if you're able to extrapolate, you are going to see what the result would be if you refine the mesh to infinity. And that is like the best guess to the ground truth. What you should notice is that for both Fun3D and the Flow 360, the extrapolated result agrees pretty well, right? And then in addition to that, a Flow 360 actually gets pretty good result compared to the extrapolated result towards the left, even at coarser meshes. So I wouldn't say this is a significant discrepancy. This is actually a very good accurate result. Does that make sense?
It does. Thank you for that. I appreciate it. Okay. Let's see. How do you control the surface T-Rex layers, like the first height, stretching rate, that are automatically added to leading edges and trailing edges by Flashpoint? That's a really good question. This kind of gets into the weeds a little bit about how Flashpoint works, and we certainly don't want it to necessarily be a black box. So the leading edge refinement that you see when we're talking about 2D T-Rex in particular, which is being applied automatically to those detected boundaries, uses the turning angle that's defined in Flashpoint surface meshing. So in that global tab, you have the curvature resolution, and by default, it's 15 degrees. That's what controls that initial height. And in fact, if you run the Flashpoint surface meshing, you get a surface mesh, you grab that domain and you go into the domain solver, you can see everything that Flashpoint has done. You can see all of the boundary conditions that it's set up for 2D T-Rex, all of the attributes and everything like that. And if you look at the boundary conditions for 2D T-Rex, you'll notice that at the leading edge, an area of high curvature, it uses the angle BC. So it sets that angle to the value that was in the global tab. So that's how you would control that initial height. And that's often more important because you want to refine to a certain turning angle, okay? Now you can change it after the fact if you want to explicitly specify an initial cell height. Again, it sets up everything for you, all of the boundary conditions. You can just go into the domain solver afterward and just change that to the wall BC type instead of angle and give it an explicit value and then reinitialize if you wanted to. Now, trailing edges are a little bit different. Trailing edges will get the aspect ratio boundary condition, and you'll see that it's the maximum aspect ratio boundary condition, and the aspect ratio is also directly controllable from the global tab as well, and the default value is 10, and the spacing is set in the spanwise direction such that the aspect ratio does not violate a value of 10. So if you wanted to control that, you could tweak the aspect ratio value. And that's a good question. Okay. All right, Chi-Chi or Fei-Lin, are there any specific mesh requirements for Flow 360?
The mesh requirements are pretty much the same as the mesh requirements for Fun3D. So we accept unstructured meshes with tetrahedral, prisms, pyramids, and hexes. Okay, so that's the type of cells we accept. And we also recently developed a rotating interface. So basically, if you have propeller rotating within a bigger mesh, or even things rotating within something that rotates, you would need a cylindrical enclosure of the rotating mesh within a bigger mesh. Yeah, that's the kind of mesh requirement we have.
Okay, and there was a question about modeling props, and I think that also answers it as well. And there was an example of that too. So, okay, there's a couple more questions, Chi-Chi, about performance. Can you be more specific? One of the questions is, can you be more specific on the numerical algorithms that justify the performance, like the Flow360's performance?
Yeah, I don't think I'm here to say specifically what algorithms we use to achieve this acceleration, but essentially it's really an obsession on strong scalability, right? So when you look at why a CFD solver cannot scale anymore at a certain number of CPUs or amount of resources, there are various things you can do to further push on that. And there are things on software we can do. There are things on hardware we can do. I mean, there are all aspects of things that we can focus on. And the Flow360 is a result of this kind of a push from a fundamental principle point of view.
Okay. Does another question is Flow360 currently limited to external aero, or does it handle shock waves and internal aero applications as well?
Yes, we can handle shockwaves actually pretty well. We validated our result all the way to Mach 2.2. And internal flows, we don't have all the array of boundary conditions required by internal flows, but we can handle a lot of internal flows simulations already. The one thing we are missing is rotational periodic boundary conditions, which is often used in turbomachinery simulations. But we have, for example, like total pressure, total temperature inlets, static pressure outlets. A lot of the boundary conditions you need for internal flows we already have, but we don't have all of them.
Okay. All right. How long does the same analysis take without Flashpoint? That's a good question. So I did a test recently for a different aircraft geometry, and I've got the values written down somewhere in my notebook. And perhaps maybe after this, I know who asked this question, and I can follow up with you. But what I can say is that meshing an aircraft kind of comes down to level of experience, right? So for me, I've meshed many aircraft in my time with Pointwise, and I have kind of a procedure down that I apply every single time. So before Flashpoint, surface meshing was available. When we were doing this totally by hand, originally the process would take on the order of a couple of hours. For something like the CRM, it probably wouldn't take that long, but for most aircraft, it'd maybe take a couple of hours to get a mesh out the back end. Now, over time, we've started implementing some more top-down approaches like synchronized spacings, like automatically applying 2D T-Rex by just picking a connector and saying go. These things, dramatically reduce that time. So where it may have taken a couple hours before, it was taking on the order of maybe half an hour to an hour, right? For a more complex, aircraft geometry. What Flashpoint does is it encapsulates all of those best practices that we have been using and our clients have been using over time for geometries like this into a push button tool. And this tool is unique in that obviously experts can use it, get a mesh, modify it to their heart's content if they want to, but it's also really approachable for people who are new to Pointwise. So what this means is that someone new to Pointwise can generate a grid that, maybe an expert by hand could do in half an hour to an hour in less than 5 minutes. And that's kind of what I've been seeing is that, this aircraft geometry maybe takes 15 minutes by hand, and maybe without any of the automated stuff, it would maybe take 30 minutes, 45 minutes or something like that, again, because I've done so many of these. But with Flashpoint, it's 1 minute. So it's a significant reduction. And the mesh that I get is often better than the mesh I could have created by hand, because there's a lot of things going on behind the scenes that I would have to sit down and pull up a calculator and figure out how to set distributions, how to set spacings, and all of these types of things, right? So it's making a lot of those decisions for us behind the scenes. So it's much quicker than doing it by hand. And if I did want to modify anything, I now have a foundation created automatically that I can then go and modify as much as I want. So I hope that answers your question. What turbulence model did you use? Chichi, I think you mentioned this, but do you want to mention it again?
Yeah, it was a Spalato-Morris turbulence model.
Okay. Is Flashpoint surface meshing structured, only structured, or can you choose unstructured? It's not structured at all. It's completely unstructured. What you're seeing there on the surface is a quad dominant unstructured surface mesh. You can switch between quad dominant and advancing front, which is all tri, and in the next version there'll be a hybrid option, which is tri mesh, but on leading edges and trailing edges you will get quads. Is there adaptive mesh refinement? So Pointwise it does include solver independent mesh adaptation. So long as a solver can write a point cloud data file, which is basically just a collection of XYZs in a desired cell size, we can bring that into Pointwise and adapt both the surface mesh and the volume mesh, and then kick out a new mesh for the solver to interpolate and keep running. There's quite a few examples of this on our website. That's a good question. Geometry cleanup. What tools do you use in Pointwise? What tools can you recommend? So geometry cleanup, I guess I could interpret this question a couple of different ways. Is at Pointwise, the company, what do we use for geometry cleanup? The answer is Pointwise. We have quite a few tools in our tool belt for doing geometry cleanup, solid modeling in Pointwise. We have the automatic tools for stitching based on a tolerance, but we also have some manual tools for doing intersections, creating surfaces, and things like that. So the majority of our geometry cleanup is done inside Pointwise, and anything else we can work with our clients to get the geometry cleaned up. Good question. Are there any restrictions on mixing concavity, convexity of the databases? For instance, if modeling an airplane with an inlet. The only thing I'll say there, and maybe that would be something where you can reach out and we can take a look at a specific example, is it comes down to quilting. So as long as you have your geometry quilted properly, and what I mean by that is quilt boundaries exist where there are hard breaks in the geometry, right? Like a convex edge, that should be, you shouldn't have a quilt that wraps around a convex edge. It should end and terminate at the convex edge. Same with like a wing leading edge where you've got a round, you need to have a quilt boundary there so that it can detect that there is in fact a curvature type boundary there. So long as those things are honored, then it will recover those particular features. So like a wing root, concave corner, you don't want a quilt that consists of both the wing and the fuselage and kind of smears over that concave corner. You want to be able to have a nice hard boundary there, and so you need to have the quilt boundary terminate at the wing root junction. Let's see here. Let's see, the Flow 360 solver looks very impressive. How does it perform on poorer quality meshes?
Well, that's a very good question. That's also one of the things we are very strong on, and also we are constantly improving on. So basically, we are really looking case by case in terms of improving our robustness, right? So, and our key principle is we want to improve constantly on robustness without sacrificing accuracy. I mean, that's a kind of a different approach as compared to, well, what is sometimes taken. So, what we can say right now is that if you give me bad quality meshes, we are more likely to converge and converge well compared to what Fun3D does. And we still won't be able to converge on some of the very bad quality meshes so essentially, like for the meshes that Fun3D can converge, we can pretty much converge.
Okay. All right. Another question is, these are all really good questions, by the way. Thank you all for taking the time to ask them. And they're still coming in. At some point, we're going to end the webinar, and any questions that are left, please feel free to email us, and we will address them then. And all right, so the next question is, Pointwise for trailing edge meshing, does it need to be blunt, or do rounded trailing edge also get treated in the same manner? Good question. Blunt, yes. We need two convex edges for those boundaries to generate that type of mesh. If it's rounded, then they'll get classified as a curvature type boundary, which is treated differently than a mapped surface. That's a good question. If Flashpoint produces a mesh with quality problems, are there any tools to improve it? Yes, you can not, well, I should mention that when you make a mesh using Flashpoint surface meshing, inside that tool, you can look at grid quality. While you're in there, you have the resolution controls at your disposal, including local resolution controls at your disposal to modify or refine the surface mesh. Outside of Flashpoint surface meshing, you have the entire Pointwise suite at your disposal to do anything you want, including going down to a single grid point and tweaking it. So yes, if there is a problem, then you have every tool at your disposal in Pointwise to go ahead and address it. Chi-Chi, Flow 360, can it do time accurate LES?
We do time accurate flow solutions, so that's unsteady, right? LES, that's we do. I mean, we routinely do detached steady simulation, so that's basically using a Rance model close to the surface and the LES away from the surface, right? We have implemented delayed detached steady simulations, and to do actual large eddy simulation, we didn't routinely do this. I mean, it requires you to have a very large mesh if the Reynolds number is even moderate. So it's not part of our routine exercise, but like actually from an implementation point of view, doing LES is not that hard. So if there is a demand, we can easily make it available.
And Chi-Chi, Flow 360 is finite volume, correct?
Correct.
Okay, that question's come up a couple of times, and I thought you'd mentioned that. Another question about quilts. I think we went ahead and addressed this one separately about quilts being merged and what's kind of the best quilting strategy. Again, really just making sure that quilt boundaries are aligned with curved boundaries like a wing leading edge, a hard, concave or convex boundary like a wing root or a trailing edge, something like that. You don't want to have quilts kind of spanning these types of feature edges, and you'll have kind of your best results with that. Is the mesher parallel? The unstructured surface, because we're talking unstructured here, Pointwise in general is multi-threaded. We're talking unstructured here. The unstructured surface mesher that is used by Flashpoint surface meshing is multi-threaded. The volume mesher currently is single-threaded. Would it be difficult to add a pylon in the cell to the CRM with the new automatic pointwise procedure? No, in fact, we have another example where we've done just that, and you can always reach out to talk to us. And the process is very, very similar. As long as it's quilted properly, then you can push the button and it'll detect the nacelle leading edge, trailing edge. It'll synchronize all the spacing so that there's no large area ratio discontinuities or anything like that. Two more questions. One is, this question I think has come up before. It sounds like it based on the question I'm seeing here. Chi-Chi, are you all trying to get to the point where you can produce instant simulations, like instant results from your simulations? They'd like to hear your standpoint on this idea.
Yeah, the goal is to get faster and faster to the point that the primary focus of the engineer is to investigate the question rather than performing the simulation, right? So that's the ultimate goal. If the engineer has to spend a significant amount of time and effort thinking about how to perform the simulation, then there is something we can do to improve on that. Ultimately, we want the engineer to ultimately completely focus on investigating the problem, improving the design, rather than performing simulations. So that's the goal, and that's why we want to accelerate these CFD simulations.
2 minutes is 2 minutes is pretty quick already. That's heading in the right direction, that's for sure. A question that's come up a couple of times as well: are there any technical papers or publications that talk about some of the details of Flow 360?
We are not ready to release the details of the implementation, but we are starting to crank out papers, basically using Flow 360 to investigate problems and the results of our solver. Okay.
I missed the first couple of minutes. Does Flashpoint surface meshing come with version 18.4 or is it separate? No, it comes with version 18.4. 18.4 was the first version that includes the Flashpoint surface meshing tool. And just to mention one more time, we kind of have been interchanging Flashpoint surface meshing, automatic surface meshing. Flashpoint in general, just so that everyone is aware, I think I mentioned this at the beginning of the webinar, is really the suite of tools that we are developing that enable automation in Pointwise. And the automatic surface meshing feature is one component of that. And you'll often hear us referring to that as, Flashpoint surface meshing, and sometimes just Flashpoint, because that's the only tool that has been released at this time. But it is meant to be a suite of tools. The next one that is being developed, and we talked about this in our live Q&A last Friday with the product planning team, is the volume meshing component. It's already pretty much automatic in Pointwise now using the create far fields tool like we used here, but the idea is to encapsulate it in a very similar workflow to the surface meshing component. So that'll be the next step. And then beyond that, it will be looking at automating the geometry cleanup portion. And all of these things will kind of sit under this umbrella called Flashpoint. Chi-Chi, what's the largest model in terms of cell count run with Flow 360, and how long did it take?
We have ran models with over 200 million grid points. I don't have on top of my head how long it takes. Feeling, do you have Oh, by the way, so this is not necessarily the longest running simulation. I mean, you can have a large mesh, but with a steady state simulation, that actually finishes faster than, for example, some of the unsteady simulations, even with a smaller mesh. And if you are looking at something with a very long time scale, you may have to integrate for many things. That usually takes far longer. And right. So, Feilin, do you have a recollection of how long these bigger meshes take?
And steady state is the question.
For steady state, I don't have any numbers for this?
Well, so my recollection is it's definitely going to be less than an hour. So something like with, and when the bigger meshes coming, we are not at so much limited by our technology, but limited by our resources, right? We are a startup company and limited by like the resources we have. So even though our technology, given more resources, can push the bigger meshes to faster speed, when you give us a huge mesh, we are then becoming limited by our resources. I'm sure that'll get better in the future.
Okay. And another question for you. Many solvers prefer extruded meshes near surfaces like we generate with Pointwise with our T-Rex algorithm for accurate analysis. Is Flow 360 accurate on fully TET meshes?
Yes, we are fully accurate on TET meshes. Although right now we don't have a wall model, so we need the Y plus to be around or less than 1. With that, even if you have a fully TET mesh, we are accurate.
Okay. All right, now we are closing in on the hour. Just a couple of minutes left. I think we've made it through all of the questions. If I skipped one, I apologize. There were quite a few. You can always contact us at our email addresses. So if we did miss your question, or you think of something after the webinar, or when the recording's available, you pass it along to some colleagues and you think of more questions, again, you can always contact Chi-Chi Wang or myself, and we'd be happy to address those. If you want to see some of these things in action, you can always contact us as well. We're happy to show you. But anyway, I do want to say thank you all once again for taking the time to watch our webinar, and thank you very much for all of the questions and interaction. We certainly appreciate it. And again, thank you, Chi-Chi and Fei-Ling, for joining me today and working on this webinar. I think it was a great application and a great way to showcase how our tools work together. So thank you very much for that. So with that, we're going to go ahead and conclude the webinar. Like I said, feel free to reach out, and we'd be happy to help. All right. Talk to you all soon.
Thank you.
All right. See ya.